Very good morning to all the students. Today I will be taking one experiment of your lab, which is on DAC interfacing. So we don't know, like another 15 days it may extend, and the lab we have taken only 4 lab programs, and we have executed it in the and seen it on the kit also. Now unfortunately we don't have kit, so but you have a software, right? So you can download that Microvision Keel software. Some of you all already have it, I guess, and some of you can go to the website of Keel and then download the version of Keel Microvision 5. Okay, so by installing this you can execute the program and check for the simulation. Okay, once the simulation results are correct, then you can once the college starts, you can directly dump it on the kit and check the output. So simultaneously we will be taking both module 4. Okay, module 3 we have completed already, module 4 and the experiments of the lab. Fine. So today I'll be teaching how to interface a DAC, okay, and to generate a triangular as well as the square waveform. Okay, so this is the explanation of we have also shared with you the experiment details. Okay, what to write in the journals, right? So this all details are there in that notes. Okay, along with that there are programs here. Okay, in whatever we have given you as a details to write it in the journal, those doesn't have the programs. Fine. So here I'll be explaining you the theory as well as the program to generate the DAC, so to generate the triangular and the square waveform. Okay, so a DAC, as the name says, it is a digital to analog converter. There is already a block in the ARM Cortex M3, that is the board what you use, LPC 1768. It has a DAC module. Okay, and that DAC module is connected to some of the ports of the ARM Cortex M3 processor. Okay, so by changing some registers and then by looking into the output pen, you can generate the triangular as well as the square waveform. Yeah. So as DAC represents, it is a digital to analog converter. So what would be the input to this? The input is a digital signal and the output will be the analog signal. So in the case of lab, we'll be seeing the output on the either the CRO or the multimeter to check the voltage values, or if you see directly on the oscilloscope, you can see the waveform itself. So whether it is a triangular as well as the square waveform. Okay, so let us see how to generate the values here, how to generate this analog signal here using the digital signal. Okay, so it is, you can see here, it's a DAC block with A out as the output, which is producing a sinusoidal waveform, and you have B0 to Bn as the inputs, which is an n-bit input here, and there are two reference values, one for the negative, one for the positive. So usually negative reference value we ground it, so it is 0, and we give some reference positive value to the VREF-P. Okay, so this is the arrangement of the DAC. Fine. So this is what the formula is given here. This is how the A out is generated, as value into V reference P minus V reference N divided by 1024 into plus V reference. So here V reference N, as I said, it will be 0. So when you substitute 0 here, V A out will be equal to value into V reference P divided by 1024. So 1024, why we have taken is because it's a 10-bit DAC. So whatever the module of DAC is present in 1768 board is a 10-bit DAC. 10-bit means it will take 10-bit of input and correspondingly it will produce the output signal. Okay, so have you gone through R2R DAC? I think you must have studied in your LIC subject. Okay, so type of DAC where you have R series of R resistors and 2R resistor connected in a ladder fashion. Okay, so that same combination used here to produce the analog signal along with the input as a digital value. So here we have digital 1024 as a 2 raised to 10, right? So maximum value it can reach is 1024. Okay, so how to program this DAC? Okay, so there are number of registers inside this DAC, and we have to change those resistor to get this analog signal. So we have where is this A out pin connected? The A out pin is connected to P026. Okay, now if you remember, we had LEDs, right? If you remember LEDs, that is P19 to 19, 20, 21, 22, 23, 24, 25, 26. So 19 to 26 pins of port 0 are connected to the LED. Now the question is how AP0.26 is connected to the A out pin, right? So here each pin of ARM Cortex M3 have 4 functions. Okay, so either they can be used as general purpose input output, or it can be used as some other functions. Fine. So here also now AP0.26 is used as a general purpose input output register in case of LED, or it can be used as a out pin. Fine. So here analog output pin provides the converted analog signal, which is referenced to as VSA, that is analog ground set bits. Okay, and now how to make this P026 as the output of the DAC instead of GPIO. Okay, so there is one procedure in ARM Cortex M3 board. There are some registers called pin select. Okay, so that is, you can see here PIN SEL as 0, 1, 2, 3, 4. Okay, and here if you have to make this 0.26 bit as the DAC output, then in pin select 1 there are 2 pins called 20 and 21. So in these 2 pins, if you put the value as 10, it will enable this function. Okay, so there are many others, like now in the next lab you will study PWM. In PWM also one pin will generate the GPIO, that is normal GPIO, and another function will be the PWM, and the third function can be something else, and fourth function also can be something else. Okay, so here P0.26, it was working normally like an LED. Now it was working like the output of DAC. To make this as a DAC output, we have to send 10 on the pin select 1 register for the 20 and 21 bits. Okay, this is prefixed, we cannot change this. 21 and 20th bit of pin select 1 should be 10. Okay, so V reference P, these are the reference voltage pins used for both ADC and DAC. So for both ADC and DAC, this is the reference voltage pin used, and usually it is VCC, that is VCC, and V reference N is a negative reference voltage. Usually we keep this as 0 volt. Okay, and then we have VDDA and VSSA. These are also analog power and ground pin to power the ADC module. There is a ADC module, right? So which has the resistors connected in series. So that module is powered using this VDDA and VCC. Usually it is connected to VCC and the ground. Okay, so now what are the registers in the DAC? Now what registers are specifically used for the DAC? So I hope you remember we had studied some of the registers called FIO set, FIO clear, FIO direction, and FIO pin. These are the 4 registers we had studied to play with the input output register. Similarly, with the DAC module, there are specifically some registers. By changing them, we can generate the analog signal. So the DAC registers which are used in ARM Cortex M3 LPC17X6 X series are, there are 3 registers: DACR, DAC control, and DAC control value. So here we are using only DACR. Okay, because these other 2 registers are used with direct memory access operation. So that is not in this section, we are not dealing with that, okay, in our syllabus. So we'll be dealing only with the register called DACR. Okay, so this DACR, in this we will be putting the digital value, we will enable the DAC, and then it starts producing the analog signal. Okay, what contains inside this DACR register? Okay, there are number of bits, that is from 0 to 31. Each register are of 32 bits. So from 0 to 5 they are all reserved. 6 to 15 are the value of value, that is nothing but input what you give, which is a 10-bit number. Then 16 is a bias, that is setting this bit to 0. Okay, selects the setting time of 1 microsecond. Setting time means what? There's a setup time, like selects a setting time of a maximum with a maximum current consumption of 700 microamperes at maximum 1 megahertz updating rate. So just don't worry about this bit 16, which we usually keep it 0, so that it produces a 1 microsecond of setting time. Okay, so this is how the DAC module contains. So you have LPC 1768 board here, then we have output pin, which is A out, which is 0.26, which produces a signal, which is an analog signal either on the oscillator or on the multimeter. So you have output here, and then you have two values as a reference for reference values, that is P and N. P is connected to 3.3 volt, as I said, it will be connected to the VCC, and V reference N is connected to the ground. Okay, so now let us see how we can generate a triangular waveform using this DAC block, and we use only the register called DACR, that is called DAC register. So hash include lpc17xx.h. okay, so this is the header file we include. Fine, then int main, we have defined one variable called val, which is under the unsigned integer 32-bit val, that is nothing but a value what we provide. And then system initialization, this is the function we use to initialize the clock configuration. Then we have LPC pincon, pin select 1. As we said, first thing we have to set the bits of 20 and 21st of pin select 1 to 10. Okay, so by making this, we will be making P0.26 pin as the analog output pin. Okay, so LPC we already had one like when we are using other registers called FIO select, FIO pin, so we use LPC underscore GPIO. So here it is LPC underscore pincon. Pincon, the full form is pin configuration. So we have to set the functions for the pins, right? So that's why we use LPC underscore pincon. It's not LPC underscore GPIO. So remember, LPC underscore pincon, pin select 1 or is equal to, why? Because some of the other pins apart from this P0.26 are connected to some of the other modules. You have seen in LPC 1768 board,